start recording. So in the video that was playing before we started the class, right, is essentially talking almost everything that we will be discussing today. So what we're going to do is we will continue discussing about currents, and then maybe we will do some tutorial 3 questions after the break, right? So towards the end of the class. But it's tutorial 3, but don't forget, just another reminder that we have quiz 1 on tomorrow, Thursday, right? So quiz 1 is only for chapter 1 and 2. So yeah, quiz 1, chapter 1 and 2, then the usual thing, right? So submit on Friday and blah blah blah, right? Standard, same as previous semesters. Yeah, no doesn't include chapter 3. First day knowing. I got typed in the announcement, right? Yeah, by the way, when I type this thing, I think it will appear in, everyone can see this, right? So this kind of thing. The quiz, where is the, I said something about the quiz somewhere. Yeah, and then I sent in a Moodle as well. Okay, so it's all this stuff here. First day. Oh, actually kind of true lah. You guys have too many quizzes all the time, right? Yeah. So, especially the math courses. Math courses have like 5 to 6 quizzes over the semester. Yeah, so that means good news, right? Easy life. So not only study for 2 chapters only, but of course, eventually we will still need to learn chapters 3, 4, 5, 6, and so on and so forth. So that one cannot be avoided. Okay. So yeah. Anything else? Quiz things. I suppose that is the important things for now. Yeah. Anyone have any question? Every subject 3 to 5 quiz. Yeah. Yeah, I know. Like math, especially math subject. Right. Sometimes got 6 or 7. And it kind of depends. Yeah, so we are talking about current, right? So current is charges flowing through a wire, right? In the video was discussing almost everything that we are discussing now, but with better animations and things like that. So if you look at the video, maybe it will help us imagine and visualize how the current is flowing, right? So for our case, we just consider conductor where the charges can move freely, and the charges can either be positive or negative charges. Okay, so this is what we stopped in the previous class, right? We have a conductor, so I will draw it as a cylinder here for now, because most wire is shaped like a cylinder of cross-section area A. And then we have electric field, so we will consider, for now, we will treat the electric field as a uniform electric field, right? So uniform electric field means I can write the vector. So if I take the horizontal axis to be my right direction, then it's just E in the X direction. Okay, and we have derived this, right? If I take the charge carrier density and how much charge per volume, and then we say that, okay, most of the particles inside are moving using some drift velocity, right? So we were discussing this previously, and then we say that once we have derived that the amount of charge that passes through the wire per second is given by this formula, and this is actually the current. So this is the electric current, is measured in amperes. And after current, we also have a current vector, because later, especially when we talk about chapter 5 and 6, we need to understand the direction of the current flowing. So we introduce a current vector. So the magnitude is magnitude, but direction is just telling us which way it's going. Okay, so that part shouldn't be a problem. And then another important thing to remember is that in the video, right, she showed an example where current is like water flowing, and water always flow from a high mountain down to a low surface. And in terms of electric potential, it is current is electric charges flowing from high potential to low potential, right? So always remember, every point of space we are able to calculate the V, the potential of a point, right? So sometimes it can be low potential, sometimes it can be high. So what we want to do is we want to understand that charges, positive charge flow from the low potential to high potential because it is repulsive force to push it to the low potential. Negative charge flow from the opposite direction, from low to high, because negative charge will experience an attractive force towards the high potential region. Then we can make charged particles stay at the outer surface. Yeah, that one is electrostatic. Then we can make some cheap conductor with high resistance in the middle and then call it with I think kind of, yeah. Yeah, probably. But does it? I don't think it matters because maybe it matters, yeah. Because like for now we are most of the time we are treating the ideal case, right? So ideal case means there's just some electric field inside, and then there's some electric field inside, and then the charge is gonna flow, right? So yes, the material is important. But as you can see, right, if you say that you fill the middle with a cheap resistor, but the current is also depends on cross-sectional area. So if you fill it with a cheap resistor and only the outer surface is a good conductor, then it's still we will realize that we do not have enough current flowing, right? So the area, the cross-section area is important, right? So yeah, maybe you can calculate the optimum, right? So what is how much cheap resistor you can fill in the middle to cut the cost and things like that. But of course the best way is the whole thing to be the good conductor, right? So yeah, okay, so because last time we were saying this is for the case of electrostatics. So electrostatic only when there's no electric field, when V is constant, equipotential, then all the charge move to the surface. But now we turn on the electric field, we turn on the electricity, right? So we turn on the power, then we are no longer electrostatic anymore. So we do not expect these to stay on the surface anymore, right? They can stay inside because they are moving now. There's an electric field now. Okay, so another factor to keep in mind. Voltage cause moving charges, but moving charge. I think so, yeah. The bronze middle. I think so, yeah. Maybe that's true, yeah. Maybe that's true. And I think maybe it will come into play when other factors are important, right? Because for right now, the factor that we're considering is just the electric field. So maybe, yeah, it's interesting to think about, right? Probably another assignment question you can use. So voltage causes moving charge, yes, but moving charge cannot cause voltage. Right now, yes, because they do cause voltage, right? Because all the moving charge, they are charges. So every point charge we can calculate the potential using Coulomb's law. That is true. We just didn't calculate it. So we're just calculating the voltage because of this, but the voltage caused by the charges, we ignore them. They are negligible. Okay, so for the moment we treat them as negligible. So as you can see, right, the positive charge flow from high potential to low potential, and this is a constant gradient. So if we take the derivative, it's just a constant number, right? And the negative sign, so it becomes a constant positive number. And the direction of current, this is also important and potentially confusing. So let me write this again. Okay, so the direction of current is going to be equal to, we follow the direction of the electric field, which is therefore the direction of decreasing potential. See, the potential is decreasing here, right? So my current is flowing this way. Okay, so it's the direction of decreasing potential, and then the direction of motion of positive charges, but it is opposite to the motion of negative charge, right? So when I is flowing this way, the electron is actually flowing the other way. Okay, so when we imagine things at electron, that is what is happening here, right? So for this case, we are taking x direction to be here, y direction to be here. Okay, so that is so these are the things that we were discussing about current just now in the previous class. Electric signal from sound signal, yeah, because speaker, you want to convert this into sound signal, so that maybe that's why you use a different material of the wire, right? So because we will learn a lot of related things later. So the current will flow through the speaker things, and then speaker will consist of the magnets, and then it will vibrate and it will cause the sound. So I don't know, maybe use gold and compared to bronze is better. We will learn more about this. Actually, yeah, let's talk about this when we come to when we derive the resistance. But before we do this, right, one more quantity that I want to define is the current density. So current density is just a current per area, right? So because this is a total cylinder, has current cross-sectional area A, and then the current flowing through is I. But sometimes what you need to know is the current per area. So it's just the divided by the area. So we will use the letter J, okay, and it is just taking the current and then divide by the area, right? So you can take the current vector as well, because you just need to include the direction. Okay, so the A here is the cross section of the wire. So and therefore, right, current density, it can also be constant or a non-constant, right? Because it's a current density, kind of like a charge density. Okay, so yeah, so let's see how everything works by considering our first example, 4.1.1. Okay, so this is a simple example just to get everything started. What we have here is, hang on, 4.1.1. Bring the thing to the front. Okay, so we have 18 gauge copper wire. So I think 18 gauge, it just means that the diameter is 1.02 millimeter, and from here we can get the radius. We know the current, and then this thing length. So find the electron density of the wire. No, the charge carrier density is given, and then I want to find this and then find the drift speed. Okay, so this one is all pretty straightforward. So let's work it out. Okay, so I can get the cross-sectional area because I know the radius. The radius is 1.02 millimeter divided by 2, right? So millimeter is this thing, right? So the current is 1.67 amperes, and then they give the power, and then they give the charge carrier density. So 8.5 times 10 to the minus 28 meter cube. Positive or minus? It should be positive, right? Yeah, positive 28. Okay, so the part A is very simple. The current density is, I just take the current divided by A, so it's just I over pi r square. So I got all these values over here. So we find that this is 2.04 times 10 to the minus 6 ampere. And oh yeah, the SI unit for current density is just ampere per meter square, right? Because the ampere divided by area. Okay, so ampere per meter square. And then secondly, I want to find the drift velocity. So for drift velocity, I will use this formula to get the drift velocity. So drift velocity is I is equals to charge carrier density. Charge of the single charge carrier and then get the A. So from here I can find the formula for drift velocity. So I just divide everyone else down. Okay, so this one, well, this is something we have calculated already, right? So I per area is just the current density. So this is J over N, and then Q is, we are talking about the electrons flowing, right? And we just take the modular sign because I want to get the magnitude. The direction is, yeah, it depends on direction of electric field. So what you find here is 0.15 times 10 to the minus 3 meters per second. So the drift velocity is actually very slow for most materials. Okay, it's a small number. So the average speed of a single charge, right, is actually moving slow. The reason why we got the current is everyone is moving, just that it's very slow. So you have the current flowing through the entire circuit, right? But it's the actual motion of the electron itself might be very slow. So that is an interesting counterintuitive kind of thing. Okay, electric guitar. Oh yeah, you guys still want to form a band, right? Yeah. Electric guitar, yeah, the principle of electric guitar like works from the concept of electric current and all those kind of thing. Which we haven't learned later, which we haven't learned now, but it's in a later chapter. Do you know how does an electric guitar work, right? Compared to the acoustic guitar or classical guitar. It's different, right? They look so different. And acoustic guitar is you have this guitar and then you have the piece of wood, and then the hole inside is because you vibrate the string, and then the string will vibrate the air, and the air vibration we will hear it as sound. But for electric guitar, there is no air, right? It's just a metal piece attached to a plastic, but you hear the sound is because of the electrical current. That's why if you play an electric guitar and you do not plug it in, right, you hear the sound, it's correct sound, but it's very soft, right? You need to plug it to a speaker. That's why. And how does it get generated? Also interesting, because on the electric guitar is you have a magnet, right, and it works by electromagnetic induction. So the string will vibrate along the magnet, and the frequency of vibration will cause the current to flow, and then that will transmit as a signal which you send to a speaker, right? So that is how the electric guitar works. Okay, any other question? Oh, Kaishan is not here, is it? In any case, let's continue first. Resistance. Yeah, speaking of electric guitar, right? Like you can make many different sounds using the guitar. Like you have distortion, and then a lot of things I don't know what's it called. You know the band Bon Jovi, right? The guitarists have this thing where on the microphone he has something like a straw, and then he blow into the straw, it actually changed the sound of the guitar. I don't know what's it called. Maybe someone familiar with music can will know better. Right. So all this manipulation and distortion is like, yeah, you are changing the current, you are doing things to manipulate the electricity, manipulate the current, and once you manipulate the current, you can make all kinds of interesting sounds. Oh, yeah, electric guitar would be a fun to play with. I never had an electric guitar. So let's talk about Ohm's law, right? So Ohm's law is, everyone knows this in the high school, right? So V is equals to IR, but this is just the high school version of it, and the actual reason why we have Ohm's law is, in fact, we won't really cover this yet. So the Ohm's law actually can be derived from thermodynamics using the method is a bit higher level, but it's actually coming from thermodynamics, because we are we need to use some statistical mechanics. We have electron flowing, right? So, and then in fact, you realize that resistance depends on the temperature of the material as well, right? And that is because it's related to the thermodynamics. Okay, so what we will do here is, our starting point is just to make use of the result coming from thermodynamics, which we don't know yet, but the main result is current density is proportional to the electric field. Okay, so yeah, so that one came from thermodynamics, but for people who did not discover thermodynamics yet, when people doing experiment, we can it was discovered through experiment also. So what we found is that a stronger electric field, it will give you a higher current. Okay, so my current density is proportional, so that means the E is proportional to my current, right? So of course it's in the same direction. So the proportionality constant is some constant which we will call rho, and this rho is the Ohm's law. Okay, so this equation is our Ohm's law, right? So this equation can be derived from thermodynamics. And this is a proportionality constant which we call the resistivity of the material. Okay. Yeah. The guitar effect, yes. Yeah, foot pad, yeah, and then distortion, you got all the foot pedal kind of things, right? Yeah, so all this equipment stuff is kind of interesting. Okay, so essentially we have our Ohm's law already, right? So our Ohm's law is right here. At the moment, it is very different from what we have known from the familiar form, which is V is equal to IR. So the Ohm's law is actually, original form is appearing like this. The reason why we use EV is equal to IR is more useful for practical calculation, right? So when especially high school lab and things like that, when you actually go to the lab, V, I, and R are something that you can measure, right? But this one is very difficult to measure. So what we need to do is to express in a form that is more convenient. Okay, so how to understand Ohm's law? So it depends on the resistivity of the material. So what we're going to do is, we shall assume that my electric field is uniform. So we assume my electric field is uniform inside wire, okay, or some material. Okay, I shouldn't say wire anymore, material of length L and cross section, which is A. Okay, and I will take this to be my horizontal direction. Okay, so I have some material, is going to be some resistor. Okay, so some electrical device, but the length of this thing is L. The cross-sectional area is A, right? So my electric field is pointing this way, so my E is some magnitude and then in the I direction, and then my current is flowing, right? So my current is flowing, so my current also has a current vector. It is current per area and also pointing in the I direction. Okay, so from here I can relate these two by using Ohm's law. So according to Ohm's law, my E is equals to rho J, right? So my electric field is equals in the I direction is equals to I over A in the I direction, right, with the rho. over here. So my electric field is equals to rho I over the cross-sectional area of the material. Okay, so this is electric field, right? But why? So Ohm's law, I want to express in the form that we want to use in high school, which is the voltage, the potential difference. The reason is because potential difference is easy to measure, right? You have the thing called voltmeter. You just touch it and then you can measure already. Electric field is difficult to measure. So what we want to do is I want to express E in terms of V, right? So this is the familiar calculation that we did many times already, right? So what is the potential difference between A and B? So the potential difference between A and B is what we call VAB. It's VA minus VB, and then it's the integral of E dot dr, right? So I keep doing this to let us practice our vector and calculus integral kind of things, right? So my E here is, my E vector is E in the I direction, and then I'm going in this direction, so it is the I with respect to dx, right? So let's say this is the position from some initial position, and this position is x plus L because I'm considering a section of x plus L, right? So my VAB is just I dot I becomes 1, right? And then what you get here is just x from here to x plus L. So essentially it's EL basically. So my E is just potential difference over L. Okay, so when the electric field is uniform, it's just the voltage over the distance, right? So I have my second equation, so I can substitute equation 2 into 1. So we substitute equation 2 into equation 1, right? So I got VAB over L is equals to rho I over A. Now we start to see something familiar, right? So I bring the VAB to this side, and then this part is rho L over A, and then I got the I. So these are constants, right? So this is constant, and we will call this we define this to be the resistance. And we will call this R. So R is rho L over A, and then we find that VAB is equals to IR. So this is the familiar form of the Ohm's law, where R is equals to rho L over A. Okay, so this is my Ohm's law that everyone knows. Okay, any questions so far? I need to, give me 5 seconds. I need to clear my nose. Liquid cooling and this one is the guitar things, right? Ohm's law high school is not a lie, it's a simplification, right? So yeah, like most of the things in high school is like all the simplified version of the thing. So it's not a lie, right? It's still this, but okay, yeah, it's a kind of a lie in the sense that it doesn't reveal what is the truth. Right, so this is the Ohm's law. Okay, so that is because Zuru was saying, right, most of the things is similar to high school, but we are learning the same things in high school, but we go one level deeper. Okay, and in fact this now I'm telling you is kind of a simplification. Also, it's also another lie because we haven't gone to higher level thermodynamics, where in the higher level thermodynamics we actually study conductors and particles flowing inside conductor, and we can actually derive this formula from the principle of thermodynamics. So in fact it's because we say that entropy needs to increase, and then we apply the second law, and then we just like manipulate and then until we get this point. Okay, so even this is still not the full picture yet, right? So you see, right, every time when we learn physics, in in a physics degree, it's like we are learning the same thing over and over again, but we go deeper and deeper underneath to reveal some secrets. So yes, this is how Ohm's law work, right? The formula that we have derived is that the resistance depends on the cross-sectional area. So when the area is small, you get this type of situation, I think, right? Kind of lah. Really? Reduce your resistance. Why do you want to do that? That means you want current to flow through your body. That will make it more dangerous, right? Okay. So yes, it depends on the it depends on the material, right? So this one depends on the material. For example, copper, right? So copper is a good conductor because the rho for copper is very small. Okay. And then talking about the bronze and copper gold wires, most wire are made of copper because copper is cheap and is kind of a good conductor. Gold is the best, right? Gold is having a resistor even lower than copper, but gold is expensive. So most of the time people don't use gold for wire. Then that's the cutting cost kind of thing. Bronze also is kind of a good conductor, but bronze is kind of expensive as well. It also depends on the length, right? So the longer, where was my picture? The longer the thing is, right, the more resistance, because we can always imagine current flow as like the water flowing, right? Like kind of like in the picture, like someone want to pass through something. So resistor is a material that is trying to block the current from flowing, right? So if the longer the object, the more thing it has to pass through, and that's why you got the high resistance, right? And then it so depends on the material, and also depends on the cross-sectional area. If the cross-sectional area is small, resistance is high, because if the area is small, the electron, not enough electron can pass through at the same time, like traffic jam, like everything's stuck there. But so if you have a wider road, wider area, a wider river, more cars can pass through. So or more water can pass through, more charges can pass through. So the higher the area, the lower the resistance, right? So it's inversely proportional. So this is the shape that we derive for a cylindrical wire of length L and cross-sectional area A. Okay, so that is the concept of the resistance. Okay, so this thing is also important, right? So this is the factor that we will use quite often. What is the SI unit for the resistor? So the SI unit is what we call the ohm. Is equal to 1 volt per ampere, right? So we call this the ohm. It's named after the Ohm's law. Okay, so yeah, that is the general idea for our resistor, right? So now we should be confident enough to start to consider electrical circuits already. So now we start to consider the DC circuit, direct current circuit, not the comics. Okay, so later in the course we will learn AC, alternating current. Okay, yeah, so the basic ingredients, where should I write? So the basic ingredients of the DC circuits are, wires, and then a resistor, and then we need a battery. Okay, so battery will be a source of potential difference, so it will cause a potential difference. Because the circuit doesn't run when there's no battery, right? Why? Because a battery will create a potential difference, VAB, and then the charges can flow from high to low potential inside the circuit. So that's why we need a battery for these kind of circuits. And then resistor is some kind of electrical device. And all electrical device will have some kind of resistance, because we want to use the electrical device to do something, right? So for example, the most standard example in your lab will be the light bulb, or heat coil or something, right? Whatever, right? So whatever electrical component that you have, right? So wire is a wire is just to connect different devices. So we assume for wire, how to say? Just say zero resistance. Yeah, it's a component with zero resistance. In the ideal case, right? So ideal wire will have zero resistance in the ideal case. V is then, which V? The voltage or the potential? Oh yeah, correct, yes. So if you notice, right, in the lecture notes and in LaTeX, the unit is non-italic, right? So we write in a straight letter. Is there a voltage? So the voltage, if as a mathematical symbol, usually in printed textbooks, if you format this correctly, it should be italic, and then the unit is straight, right? So it's not italic. That's a very tiny difference. Yeah, that's true. AC also stands for aircon, right? And AC/DC is also a band. Okay, so the basic picture is, yeah, so we have this, right? And then let's explore this in a bit more detail. So let's say I have a battery, right? So I have a positive terminal, negative terminal, right? So a battery will have a potential difference between the terminal. Excuse me. Right, and then I connect this to a wire. Okay, so I connect this to a wire, and then I have some kind of thing that is a resistor, and then I connect this back, right? So maybe this is a light bulb, right? So there's lights coming on, but the length of this thing is R. So from here we can calculate the resistor is just rho L over A, right? So the cross-sectional area is A, right? So I got the resistor over here. But let us keep track of what's happening with the potential. So I'm going to call this potential at this point is VC. The potential at this point is VD, okay? So I have two parts of the wire, right? So this is from here to here, this is a single wire. I will call this part 1. This part I will call this part 2, and then the other wire is part 3, right? So let's see what's happening here, right? So let's look at wire 1. Okay, so wire 1, let's use our Ohm's law for each component of the wire, because when we derive, right, so it is derived for some current flowing through some material with some resistivity. Okay, so our wire 1 is, we assume it is a material that is low resistance, so we approximate to 0. So what is happening here is, what is the potential difference across wire 1? So the VAC is equal to IR. But for the wire 1, it is 0 resistance, so there is 0 potential difference between VAC. So even though this is no longer electrostatic, but for materials with 0 resistance, it is still the same potential along the wire. Okay, so the same potential along the wire. So we conclude that VA minus VC, this is notation for VA minus VC is equal to 0. So in other words, we conclude that VA is equal to VC. So these two are equipotential. So this whole part is equipotential all the way along the surface. Right? So wire is still equipotential even if it's not electrostatic. Okay? So wire is a conductor of zero resistance. Okay, but for resistor 2, okay, so resistor 2 is VCD is equals to IR, right? R is rho L over A, right? And because this is IR, so it's rho L over A, so none of these are 0, so this term is not 0. Okay, so this term is not 0, so yeah, so VC minus VD is not 0. And then we go back to wire 3, section 3 is, what is the potential difference? VDB is equal to IR, but this is 0 resistance. Okay, so in other words, VB is equals to VD. Right, so now we can equate the two. So you see that VC is the same as VA, right? So VC is the same as VA, and VD is the same as VB. So the potential difference across the resistor, what is the potential difference across the resistor, right? So it is what, VC minus VD, right? And then this is equals to IR. So I have shown you that VC is equals to A, and VD is equals to B, is equals to IR. So it's the same as VAB, IR, right? So that's why we have the potential difference across the resistor is the same for the battery if it's just a single component over here, right? So this is the potential difference across the battery. Right, so that is why yes, in high school we say Ohm's law, V equals to IR, and we immediately jump to say that the V here is the V of the battery, right? And now we really understand the deeper reason why is we calculate the potential difference, right? So for an ideal wire, they are systems with zero resistance, so equal potential, then VC, VD, and then equal potential. So by the equation, we can equate everything, and we say that the potential difference on the battery is the same as the IR on the circuit. Okay, so that is yeah, we are, so see, it's still the same thing we learned in high school, but we are digging a bit deeper. Okay, but now that we so another thing, right? So this picture is very complicated to draw all the time, which is why we have the circuit diagram. So instead of having this picture, we will just draw this type of situation. So the resistor is this symbol. Okay, so this is the positive terminal, this is the negative terminal, right? It will have a it will contribute a potential difference of VAB, and then the resistor will be having some resistance R. Okay. Actually, in fact, right? Yeah, we can mention this in another way. So because later we will talk about Kirchhoff law. You guys have learned Kirchhoff law in high school before, right? And we can start to derive Kirchhoff law in this case also. So let's go. Yeah. So let's go around the loop. We sum up the potential difference. Okay, so yeah, so we have VAB plus VBD plus VDC plus VCA. In Kirchhoff law, we say that this is equal to 0. So VAB is some potential of the battery. There is no potential difference across the wire. And then VCD is the negative of this thing, and then this is still 0. And this part is IR. So we again derive V is equals to IR. Okay. So we got something like the Kirchhoff loop rule. And another thing that we have assumed, right, is that I didn't say this explicitly, but we kind of assume that the current flowing through everyone here is the same. Okay, so this is current AC, and then this is current dB, right? So this is because it's a conservation of charges. Okay, so the current in this section is the same current in this section and current through every section. Okay, so we just call this I. So this is another Kirchhoff law. Later we will know this as Kirchhoff junction rule. Okay, so hopefully it's not too confusing so far. If if C in R plus A equals to D, D equals to A. I don't get it. What's this? R to the power positive. Is different from high school. Oh, yeah, sometimes we use the square as well. Yeah. Yeah, that's true. In fact, our textbook, the textbook that most of us we see in the for example, the Young and Friedman, is this. I think I know the reason why lah. Because if you use software to draw, right, this picture is very hard to draw. So this one is like you can Photoshop, you draw the square easily done, right? So that is one way, that is one reason. R positive. Oh, real number. Okay, real set of real number. Oh, yeah. So you mean this R, the R, right? So this is different from R. Okay. Next thing to talk about, right, is the voltage. We have a bit of a fancy term for this. Is we call this the electromotive force. Is sometimes we just say it's EMF, right? EMF. It is the voltage source of the battery. And even though the word force is being used here, is for historical reason. Now we understand, and now we are careful to distinguish the differences between force, field, voltage, energy, and things like that, right? So this is not really a force. Okay, but rather is a source of potential difference. Okay, so for the case of ideal battery, right, for ideal battery, then the EMF is equal to the potential difference between the terminals. Okay, so so the battery, we use this symbol, right? And then battery is usually inside a box, right? So, or some something, right? Some container. And then the terminal is A, the terminal is B, right? So the EMF symbol, we will use this, right? So for the ideal battery, the potential difference across the battery is just this, right? So this is for the ideal battery. Okay, why I say ideal battery? Because there's gonna be a non-ideal battery, Okay, so for the non-ideal battery, there exists an internal resistance. Okay, so we have been assuming the battery has some perfect source of EMF, right? But sometimes when you use a material, right, the battery can get hot. In fact, for handphone, right, those low quality battery, you feel very hot inside your pocket also, right? And that is because battery also can get hot because there is some resistance happening inside. So so we will treat this as another resistor of resistance R. So what is happening here is, okay, so my battery now, right, my battery is like this, okay, and what is the potential difference across the terminal? So this is terminal A, right, and then this is terminal B. What's the potential difference? So ideal case, I have a battery that is having a source of EMF E, right? But if it's not perfect, then it will be having some internal resistance over here. Okay, so the potential difference across the two terminals is EMF, but it will be reduced by IR. Okay, so let's say there's some current flowing here, right? So V is equal to if there is no resistance, then fine, right? Potential difference is the same as the EMF, but if there's a R here, then the effective voltage battery has been reduced. So this battery is not as powerful as the ideal battery because the resistor will take away some of the power. How do we measure the EMF? So yeah, it's like a chicken and egg problem, right? So when the battery claims to have some voltage, okay, 12 volt, then you measure 12 volt, then it's fine. And one way is to use Kirchhoff's law. So you use a circuit, then you use a circuit in series, right? So if you put another resistor, then you can measure the current, you measure the total resistance, and then you can identify the value of R. So once you get the value of R, then you plus this to get the EMF. So that is one way to measure, right? So to measure the EMF is just VAB plus IR. So you just need to measure the current and measure the resistance using Kirchhoff's law and all that kinds of things, right? So do the experiment to measure it. So yeah, so now we are ready to start handling circuits already. So I'm going to talk about a few components that will appear in DC circuits. We will solve all kinds of DC circuit problems later. And then after that, we will talk about the power. So firstly, let's talk about components. Right, so we have a resistor. Or as Yiming pointed out, sometimes the textbook use this symbol. So this is the resistor. Okay. And then the battery, right? So the battery is I will draw it like this. So the longer side will be negative, right? So this is the battery. So it is a EMF source. It will be the source of potential difference, right? So circuits with no battery doesn't work because if there's no battery in the system, everyone has the same potential, so the current doesn't flow, right? And then just now we talked about the non-ideal battery with the internal resistance, right? So this is the battery with internal resistance. And then sometimes the question will talk about voltmeters and things like that. So this one will be more relevant if you do lab, right? If you do experiment. Voltmeter, they use the symbol V. And then you attach the voltmeter terminals between 2 points, right? So this voltmeter, it will give you a reading, some number, right? And yeah, so this is called the voltmeter. So the voltmeter measures the potential difference between its terminals. So it is some device, right? So you know, to measure what is the potential difference, so the voltmeter has 2 rods, right? So usually you will see in most lab is some yellow color like thing with some reading in the front, right? Is some adjusting things, and then you have is 2 rods, and then you just touch the 2 rods between any 2 points that you want to measure the potential difference, and it will tell you what is the potential difference between the 2 terminals. Okay, so that is the voltmeter. And then another component is the ammeter. So the ammeter is just measuring the current. Okay, so measures the current passing through it. Okay. Yeah, so these are the components. So yeah, has anyone watched Apollo 13? So I remember a scene, right, in Apollo 13, right? The spaceship is very low on power, and then but they want to turn on some important components, and then they want to make sure all the total current of the system is less than 13 ampere, right? I still remember it's like 12 ampere or 13 ampere, something like that. So you need to choose, you need to decide what component to turn on so that it doesn't consume less than 13 ampere, because after the explosion for the Apollo 13 spaceship, they lost a huge source of energy already, right? So they need to be careful to how to turn on the devices. Okay, so yeah, I guess now is a good time to take a break. So let's take a 10 minutes break, and then when we come back, I will talk a little bit about the power, and then maybe we shall do some capacitor tutorials. Okay, so let's take a 10-minute break. Oops, why this? Replace our class on the Thursday, and we shall do the midterm on the Thursday. All right, so we were talking about this on the first day of the class, right? So yeah, our midterm, I think our tentative plan is to go from chapter 1 to chapter 4, which is the chapter that we are now, right? So at least until chapter 4, because most likely we can finish that. We can finish all this chapter by next week, and then still not yet the midterm. So you slowly study chapters 1 to 4 for the midterm. Yeah, so that's the midterm kinds of things. Yeah, we cannot avoid, right? Every course must have a midterm, must have quiz, must have final exam. So it cannot be avoided, right? Every single course has like that. Let's talk about power. So that's the next thing to talk about. We talk about resistance, currents, and the next thing is P, right? Power. So we have kind of already touched upon power in mechanics. So mechanics, we define power as the rate of work done, and we are going to do it the same here, but now the work is being done is related to charges, and it's still about the rate of energy change, the rate of energy transfer, and therefore we can get the rate of work done in this way. Okay, so yeah, so what happens about power, right? So we have we talk about a current passing through a resistor, right? So a resistor is some component, right? Is some component is like, let's say it is a light bulb, or let's just imagine a light bulb, or it could be anything else, but let us treat it as a light bulb. So there's a current flow through a light bulb of resistance R. So every electrical device has some kind of resistance. Why? Because the energy of the charges that is flowing through it, right, it will go through a resistance, and this resistance will absorb energy out of the system. That's why the electrons will have a drop in potential. So once you drop in potential, then where does the drop in potential energy goes, right? It will be used to do something by the component. So if it's a light bulb, the energy will be converted into light, and that's why we use it as a light bulb. Maybe instead of a light bulb, you have some heater, right? So if you want to boil water, the electric boiler, right? So the current will flow through the boiler, and then it will be emitted as heat. It will go into your water to boil your water, right? So that is also another device of having some resistance. Okay, so basically what happens is when a charge carrier flows through a resistor, a charge carrier flows through a resistor, the potential drops by V equals to IR, right? So potential drops by V is equals to IR, right? So what does this mean in terms of the charge, right? So this means if the charge carrier has a charge Q, right? So a charge Q has decreased its potential energy by an amount. Well, the potential energy is Q times the V, right? So when I pass through it, it will decrease by this amount, right? So then we ask the question, where does this energy go? Okay, so that is what we want to calculate, right? So we want to calculate the transfer of energy, and we have learned in mechanics in our previous course that the transfer of energy is basically the work done. Okay, so we can now try to calculate what is the transfer of energy during this process. So as charges flow through a resistor, the potential energy drops, reduced by Q times V, right? This V is V equals to IR, right? So we can calculate how much energy is lost. Of course, we can. What we want to do is energy loss per time, because we are talking about current. So current is always flowing all the time. So what we have is not just the total charge, but actually what we only have is the charges flowing per second. That is the current I. So in a total amount of charges flowing per second, how much is the energy transfer per second? And that is where we can calculate the power. Okay, so let's calculate. We do it our usual way when it comes to current, is we look at a small time interval dt, right? So during a time interval dt, right, the amount of charge that pass through the resistor is what? Well, I want to know how much charge has passed through the resistor. Well, I know the current is I, so I times dt, right? So I is current per second, so current per second times the time interval, it will give you the actual charge that has passed through. So what we do know is now we can calculate the work done. It's actually the work done by the resistor, okay, during this process. Well, I can calculate the work done. So the work done is the transfer of this energy. So I just take the potential drop across the resistor times the Q will be the energy that is lost as the charge flows through the resistor, right? So a charge is dropping through the potential as it passes through here. So when it passes through this resistor, the potential energy decrease, right? So if I take that charge times the V, the potential difference, I will calculate the energy difference, right? So I will take the energy difference like this over here, and this dq is given by I dt, so I can substitute this inside, right? So this is just equals to V I dt. Okay, so then what we can get is this we can only calculate for a certain time interval because charges is flowing all the time, so per time is just dw dt, right? So is the Vi. And what does this mean? This is actually the power, right? So power is the rate of work done, and power is equals to Vi across the resistor, right? So from I should have said that the potential difference across this is V. So across this is V, right? And the current is I. So if I know my potential difference is V, and if I know my current is I will know the power generated by this resistor. Okay, so this is P is equals to Vi. This is another formula that we probably learned in the high school, right? One of the simplified things. We learned the simple things like Ohm's law, V equals to IR, and then P is equals to Vi. So what now we really understand, right? Because we understand from the beginning related to charges and potential. In terms of this is the rate energy rate of energy, we shouldn't say dissipated, but rate of energy, yeah, dissipated from the flowing charges. Flowing charges. Okay, so then this energy is used to power our electrical devices. So this is the whole point why we have circuits, right? Why we design circuits and things like that. Why we need electricity, right? So using the reason why is because this electricity will pass through something with a resistance, and this resistance will take out energy out of your flowing charge, and this energy will be used to convert to be light, right? Or if you want to have an electric heater to boil water, this energy will be generated as heat, right? Because heat is Q, right? Heat is just energy, right? So you generate it as a thermal energy, or whatever components that we can think of, right? So all our electrical components is using energy to do something. So that is why electrical devices work as a resistor. Okay, so resistor is two things, right? A wire has low or zero resistance because we don't want to use wire to generate energy yet. That's why for wire is I want to connect two parts, we need to have a low resistance. But for the actual electrical components that we want to use, then it has a non-zero resistance because we want to take out the energy and use it to do something. Okay, so it's not to say every time that R0 is good. It depends on what is your component, right? A wire should have low resistance because we are not using wire to generate energy, right? But the end of the wire connected, right, your speaker has a resistance because it will use the energy to convert into sound and all that kind of things, right? So it depends on which part of the device that we are talking about. Okay, so that is the thing, right? And I think in most one way to remember this formula is I think it's being taught in most high school is that power is very important, right? So we remember PVI, the formula. Power is very important. The formula. Okay, but also right. Okay. So P is equals to VI, but V is equals to IR. So I can actually substitute this inside. So I got P is equals to I square R. So I have another formula over here, right? But also I is equals to V over R. So I can actually substitute into here also. So this is V square over R square R. So P is equals to V squared over R. So I have several different formulas for power. So we start with P VI, but using Ohm's law in different ways, I get a few different formulas. Depends on what information we have, right? So we have several different formulas. This is page 6, page 7. Okay, any questions so far? Okay. So everyone can still hear me, right? Wait, what did I press? Yeah, so essentially these are the basic things related to electrical circuit, DC circuits, right? And so far everything that we have been covering is one battery, one resistor, simple model. We are understanding the fundamentals for now. So the next thing will be to start to understand more complicated circuits, so multiple resistors, so resistors in parallel in series. Then the formula, right? You already know the formula is opposite from the capacitor formula, and we will derive this maybe next time, right? I think for now what we probably should do is to go back to capacitor a little bit and start to look at some tutorial questions. Okay, so let's look at capacitors. Yeah, we are kind of taking it easy, so I can slowly do each question one by one. So let's start with tutorial 3. Let's start with question 1. We have okay, so I have a parallel plate capacitor that is 2.5 millimeters apart. So this is a D. Each carries a charge having this magnitude. It's in vacuum, so we have no dielectric here. The electric field is given. What is the potential difference? What's the area? What's the capacitance? Okay, so this is the common type of question that we encounter, is just to make sure we know how to use our various capacitor formula. Okay, so according to the question, right, we are in tutorial 3 now. So question 1. Okay, so question 1 is I have this distance between the parallel plate capacitor is 2.5 millimeters, right? And then the charge on the capacitor is 80 nanocoulomb. So nano is -9, right? And then the electric field given is 4 times 10 to the 6 volt per meter. Okay, so the first thing that we want to do is I want to find potential difference between the two plates, right? So I have parallel plate capacitor, right? So the distance between the two of them is D, right? And then the potential difference is VA VB. So the potential difference is VAB is defined to be VA minus VB, right? So we want to find this. Okay, so how can we find the potential difference? What information do we have? We only have this information, right? So usually, yeah, then using this information, well, VAB, I can make use of this electric field. So this is the integral of E dot dr. So for a parallel plate capacitor, the electric field is uniform, right? So my electric field is uniform, having some magnitude E and I. Okay, so in electric field is uniform for parallel plates. Parallel plate capacitor. Okay, so which is why I can do this calculation, integral of E dot I dx, and then E itself is just the magnitude I dot I and then dx. Okay, and then the x doesn't really matter because it's just some initial position and then initial position moving to the right by d, right? So that is why we have VAB is equals to E times D. Okay, so again, this is another simple formula that we kind of memorized in high school, and this is only true when my electric field is uniform. So E is a constant number. So for other problem, right, when E is not a constant, then we need to be careful with the integration. But now we can do this. So it's 4 times 10 to the 6 and then 2.5 millimeters. So the value is 10k volts. Yeah, so handwriting is difficult to italic, and so VAB, this is volts. So the unit has the same letter as the symbol. Okay, so yeah, so we got this now, and then what is the capacitance? So the area of each plate, or the capacitance. Actually, yeah, we can solve both parts at the same time, basically, right? How do we get the area? Well, what we do know is the formula, right? The capacitance formula, if it's in vacuum, is the area over D, right? So can I get the area? I need to know C, which I don't know yet, right? So how do we get either of these? Well, one thing we can do is I know the voltage and I know Q, right? So I know the voltage, I know Q. So knowing VAB and also Q, right? So VAB I know, we can use Q equals to CV, right? So from here I can get C is equals to Q over VAB. Okay, and I want to get the area first, so I can just do this. So my area is just QD over epsilon VAB. So if I put in all the values that I know, right, put everything in, the area is 2.26 times 10 to the minus 3 meters square. Okay, so this is the area, and once I got the area, the capacitance is epsilon A over D. So I know everything now. The capacitance is 8.00 times 10 to the minus 12 F. Okay. Gauss law to calculate the area. Actually, yes. Yeah. Also can. Yeah, because from Gauss law, we can calculate the flux, right? So E times A is equals to the charge enclosed. Can we do that? Yeah, we can, right? So if I use Gauss law, right? So if I take this, let's try to use Gauss law, right? So yeah, let's draw the Gaussian surface like this. So the like this over here, right? So according to Gauss law, we have integral of E dot dA is equals to Q enclosed over epsilon, and then what I want to find is the A, and then I know the charge enclosed is just the total charge given, right? So yeah, we can get it. It will give the same number probably if I didn't do any mistake in this reasoning here. So yes, Gauss law is fine. Yeah, so I guess that's probably why the textbook asks to find area first, then find the capacitance, right? Because in the way I do it, I found the capacitance first and then can get the area later. So the reason why we can use Gauss law, right, is actually they are related. If you recall, we derive our capacitance formula starting with Gauss law in the first place, right? Get the electric field, and then once we got the field, we get the potential difference, and then from there we get the capacitance. So it's actually the related method. Okay, so let's do number 2. What time are we now? 10:30. Yeah, still pretty early. We can just do number 2. Right. We are still relaxing and chilling and going with the flow. So question 2. 10 microfarad capacitor but we have circular plates. Okay, it's connected to a 12-volt battery. Find the charge, and then all this kind of thing. So find the charge, and after finding the charge, we want to see what happens if I double the separation but while remaining connected to the battery. So this is an important concept to keep in mind, right? So let's do the first part first. The capacitor is 10 microfarad. So micro is 10 to the minus 6 F. The potential difference across the plates is 12 volts. So let's do the easy thing first. The charge is Q equals to CV. So if I multiply the two, I got 1.2 times 10 to the minus 4 coulombs. Okay, so like this, right? And then yeah, so I want to know what happens to the charge when I do a separation. So I need to know, well, okay, so VAB, this is a parallel plate capacitor, right? And this capacitance depends on the separation distance. So if I change my separation distance, I will change C. So to see how it changes, I will write the formula explicitly like this. Okay, so my Q is just epsilon A V over the distance, right? And if I want to double my new separation distance is twice of my original, right? Then my new charge, okay, oh yeah, important thing to discuss. Why new charge? Because the capacitor is still connected to the battery, right? So it's still connected to the battery, so the charge is not constant, but the potential difference is constant. Okay, so we are still connected to the battery. Okay, because it's important, because sometimes you have another question where you disconnect from the battery, then it's a different story, but we are still connected to the battery. So VAB is the same, and then this will change. Okay, so that means I will use the same value for VAB. Okay, so my new charge will be epsilon A VAB, the same, but my new distance is 2D. Okay, so the answer is just half of it, right? So epsilon A VAB over D. So this is my previous charge. So my new charge is half of my original charge. Okay, so if I connect this to a battery, and if I can separate the discs, it turns out that I will reduce the charge on the battery, on the capacitor. Okay. On the other hand, still connected to the battery, but the radius is double. So if I increase the radius, what will happen? So this is a parallel plate capacitor, right? So I got parallel plate. And then the area is pi r square. So the area of the capacitor is pi r square. So if I use my new radius is twice of r, then my new area is just pi 2r square. So it's 4 times, right? So it's 4 pi r square. So it's 4 times my original area. Okay, then still connected to battery, so the VAB is the same, the charge changes. So my new charge is just well, my formula was epsilon, but I use my new area. This one is the same. The distance for this problem now is the same, so it's just epsilon 4a VAB, right? Distance. So my new charge is 4 times my original charge. Okay, any questions so far? So yeah, so we are at the first few questions, right? So everything still feels pretty easy. The last few questions is the harder one, so I'm gonna save that to next week. So yeah, question 3 now. And then this one will be, yeah, it will start to get interesting, right? But for now, question 3, we are still talking about a spherical capacitor. It contains a charge of 3.3 nanocoulombs when connected to a potential difference. Plates are separated by vacuum. Inner radius of the outer shell is 4 cm. I want to calculate the capacitance, the radius of the inside, and then calculate the electric field just outside. So if you are familiar with spherical capacitor, it's pretty easy, right? So remember, what's a spherical capacitor? Spherical capacitor is the distance inside is a RA, right? And the outer sphere is RB, okay? And the electric field is in the radial direction, right? So for a spherical capacitor, the electric field is not a constant, okay? So should I do a revision on deriving the spherical capacitor? Yeah, let's do that very fast, right? Because this is important. Here is 4 pi r squared. But I think it's boring lah. In any case, the spherical capacitor, we have derived this in the lecture notes already. So the capacitance we have derived was 4 pi epsilon RA times RB, and then RB minus RA. Okay, so this is the capacitance of a spherical capacitor, right? So for this question, we are given the charge, which is 3.3 nanocoulombs. The potential difference between the two plates are 220 volts, and then we only know the RB. So I only know the outer radius. It is 4 cm, so 10 to the minus 2 meters. Okay, so the first part is I want to calculate the value of C, right? So there's different ways to calculate the capacitance. If you use this formula, I cannot, because I don't know the RA, right? I cannot use this yet. What I do know is Q and V, so I can use C is equal to Q over V. So it's just dividing these two numbers. So the capacitance is 1.5 times 10 to the minus 11 F. Okay, and then from here I can count. I want to find RA. So finding RA, I will use the formula is 4 pi epsilon RA RB minus RA. Because I know RB, I know C, so I know everything here. So I can use this to get RA, right? So just simplify this equation. So C times RB minus C times RA is equals to 4 pi epsilon RA RB, right? So if I bring this over, CRB is equals to 4 pi epsilon RB plus C RA. So this is a general formula for RA. It's just CRB over 4 pi RB plus C. So I know all these numbers, so I can punch everything in. It is 3.09 cm. Okay, and then finally I want to calculate the electric field. So the electric field inside the capacitor was 4 pi epsilon R, right? So at the distance R equals to R, I want to know R inner or outer, I forgot. Just outside the surface of the inner sphere. So at R equals to RA, my electric field is just Q over 4 pi epsilon RA. I forgot the square, right? But once you get everything, you can get the value, which is 3.12 times 10 to the power 4 newtons per coulomb. Okay, so for capacitor question, at least the basic ones, right? Most of the time we spend is just using the formula, manipulating around and get this. Sometimes you get a more challenging question is derive the capacitance of a spherical capacitor or a cylindrical capacitance per length, that kind of thing. So you just need to be careful, you know, see what information you have and see what you can derive from it. Okay? Yeah, any questions so far? Wait. Okay, it was frozen for a bit. I don't know what happened. Okay, so 10 more minutes, so we can probably do this couple of questions. Let's look at question 4. Yeah. So question 4 goes like this. Q4, right? So in this figure, all the capacitance has 4 microfarad, and then the potential difference between A and B is 0.28. So I want to calculate the charge on each capacitor. I want to calculate the potential difference across each capacitor and find the potential difference. So this is kind of a tedious problem, but it just let us practice and understand all the concept and how to get the potential differences correctly. So let me just draw the picture step by step. Right, so firstly, all the capacitance is 4 micro. So it is 4 microfarad here, 4 microfarad here, and then down here is 4 micro, and then it is attached to another 4 micro here, and then continue on. So this is point B, this is point A. So the potential difference between these two is, what was it? My memory is getting bad. 28 volts. Okay, so you just, well, first of all, let us simplify this problem by reducing the circuit. So this is a capacitance in series. So capacitance in series means I can find the equivalent resistance by taking 1 over 4 micro plus 1 over 4 micro, right, inverse. So this is 2 over 4 micro, this is 1 over 2 micro inverse. So my equivalent resistance is 2 microfarad, right? So it is the same as doing 2 microfarad, and then this is 4, and then this is 4, right? So this one I can reduce further. Sorry, it's out off screen, right? So this one, the equivalent resistance is 2 plus 4, so it's 6 microfarad, right? So it's the same as becoming this. Okay, and then now this one is series, so the equivalent resistance is 1 over 6 plus 1 over 4, so the equivalent resistance here is 12 over 5. Okay, so I got all the intermediate steps, but well, we haven't really answered the question, right? So what question are we supposed to answer? The first thing is I want to find the charge on each capacitor. So I want to find the charge. So for the charge, right, Q is just equals to CV. Okay, so yeah, so by the way, this is the same as 12 over 5 micro. Okay, so yeah, so if I take the equivalent resistance, right, so the total charge is Q is equals to C equivalent times the potential difference. So it's 12 over 5 micro times 28. So the total charge of the system is 67.2 micro coulombs. So this is the total charge, but actually where does the charge go? So let's look at this for a moment. Okay, so this is the charge of the system, and another thing to remember is that capacitors, what we have derived in the lecture previously, right, is that capacitors in series have the same charge. Okay, so capacitors in series have the same charge. So what does this mean? Okay, so I have reduced it here. I calculated a charge. So this whole thing, right, has an equivalent capacitance of 6, right? I have reduced this already. So these two are in series. So according to this calculation, this capacitor is having 67.2 microcoulomb. So therefore, this is 67.2 microcoulomb, right? This 4 is already a capacitor by itself. So I have answered the question for this 67.2 microcoulomb. Okay? Make sense? Right? So this equivalent capacitance is having 67.2. Okay, so I found the charge on the fourth one. But how to get the other one? Okay, so this effective capacitance is actually this in parallel and it's actually this, right? So let me go back one step. I want to determine the charges of these two capacitors, right? So how to get this? So let's look at this part. So this is step 1, this is step 2, this is step 3, and then the final step is this, right? So let's look at step 2. So what we have here is that 2 micro, 4 micro, and then this is 4 micro, right? So we have found that this is having 67.2 microcoulombs. So how to get the other charges? Okay, so well, let's look at this way, right? So let's look at the potential difference. The potential difference across from here to here was 28, right? And I can calculate the potential difference using this. So the potential difference is just take Q equals to CV, so this is Q over C, right? I know the Q and I know the capacitance. So the potential difference across this is wait, I don't have the figure, so I need to 67.2 divided by 4. So this is 16.8 volts. Okay, this is 16.8 volts. So from here, 16.8 volt, the potential difference is going to be 28 minus 16.8. So 11.2. Okay, so this potential difference is 11.2. Right? So I know the potential difference is equal to 11.2. Then from here, I can now get the charge. So Q is equal to CV, right? So using Q is equal to CV, so this is 2 microcoulombs times 11.2 volts. So this charge is 22.4. And then similarly, I can get this charge. Q is equal to 4 micro. And then the potential difference is this. So this is 44.8. Okay. So now this 4 micro capacitance, right, is just this alone standing here. So this answer turns out to be 44.8. Okay, 44.8. And then finally, how to get these two? Well, these two, the effective capacitance is 22.4, but capacitors in series have the same charge. So if this is 22.4, then both of them is 22.4 microcoulombs. And this is 22.4 microcoulombs. Does that make sense? I don't know. I don't know whether my method of showing you these steps is clear or confusing to you guys, but at least this is the way I keep track of all the information as I do the calculation. At least this way we can get all the charges on the capacitor correctly. Alright, so I got the capacitance here. Okay, then from here we can also get the potential difference. So what's the potential difference? So the potential difference is 16.8 volts, right? And then this is in parallel, and we have calculated that the potential difference across here is 11.2, right? But this total is 11.2, so this plus this should be 11.2, but I can get the voltage by using the formula Q equals to CV. So the voltage is just the charge, 22.4 divided by 4 microcoulombs, so this is 5.6 volts and this is 5.6 volts. So this plus this gives you 11.2. That's why the parallel circuit should have the same potential difference, right? That's what it means by parallel. Okay, so yeah, so I think we have everything already over here. So is everyone following so far? Or do you guys find this boring? Or falling back asleep? Yeah, so I don't know. Yeah, so I'm just asking whether you guys understand what I was talking about, because this is a this kind of question, right, is difficult to present to people, right? Because everything is kind of, at least the way I solve it, everything is going on inside the head or inside your random scribbling, and it's not appearing in order, right? So I do it this way, and then I go back to on the original picture and put the things here. So I think it might be confusing, but the final answer are all here. See whether, if you do not want to use my method of solving this, these are the final answers. So see if you can get the expression in your own way, right? Because solving this question, there is no best method. Everyone has their own personal method that is fast as for this type of question. So as long as you get the correct answer, it should be fine. A bit like French bread. Oh, so the French word for pain is bread. Really? It's similar. Yes, it's too many things to calculate. It is unfortunately the case. Yeah. And it's only like 4 things. But yeah, 4 things is a lot, because 4 charges, 4 potential differences, and things like that. Yes, it is true. It's similar to high school. It is similar to high school, right? But for this kind of problem, it's similar to high school. But later we will solve the things that's definitely not in high school, right? The last few questions is the more challenging ones. So we run out of time already, so we shall do that in the next week. Okay. So yeah, if there's no question, let me stop the recording.